Welcome back, everyone. This is the continuation of our paper recycling course, and what we're going to talk about today is paper recycling mill wastes. This is a topic that's really important. Even though we're doing recycling and we're diverting some materials to landfills, there are still environmental consequences to our recycling process. In fact, we do generate a lot of waste, and that's what we're going to discuss today, how we handle it and where it comes from and what its composition is. Okay. First thing is that we need to understand that there is no way that we're going to recycle paper without any waste. There are very rare occasions when you have perhaps pre-consumer waste that's considered maybe as a pulp substitute with no ink on it. Let's say envelope clippings that have no adhesive on them. Those kind of things might not have any waste, but in most cases, especially with post-consumer recycled material, we're going to have quite a considerable amount of waste, and that's what we'll talk about today. Just as an example, and this is a little exaggeration, but this was published in Progress in Paper Recycling in 1996, Volume 6, Number 1. Here's 4 different de-inking mills that are in the United States with, we've just put abbreviations for them. But you can see that these mills are taking mixed office waste, de-inking it, and making printing and writing grade quality papers out of them, high brightness, low mechanical pulp. Yields around 60–70%. So we're only getting about 2/3 to 3/4 yield. So we're getting 25 to 33% waste. And then if you look at the amount of sludge in oven-dry tons per day, you can see that it is very, very high, 340 oven-dry tons per day. When we think about sludge, we need to realize that typical pressing can only get us to about 50% solids. So that 340 oven-dry tons per day really represents 680 wet tons of sludge per day. So you can see that basically that AFR mill, it was producing about 650 tons of product per day, and it was producing about 680 tons of wet sludge per day. So it's actually producing more sludge than it was product. Interesting thought. This is somewhat of an exaggerated kind of example. These were measurements taken in the mid-90s, and they were examples of mills that were really trying to make clean pulp with the technology available in the 90s. And it would be, some of these are reasonable, but some of them are very low yields. Okay, so let's just kind of go over what are our major types of waste that we can get from a recovered paper mill. The first category, stock prep rejects. That has, instead of stock prep, you should probably think of it as around the pulper and the cleaning and screening, the coarse cleaning and screening, and maybe some finer screening. But what you'll get is ragger tails. Remember, ragger is the wire and the plastic films that we pull out of a continuous low consistency pulper. Drum rejects, these could be after a continuous pulper, the pulp is sent to a coarse cleaning operation that ends up with a drum, dewatering some plastics and things as the drum rejects. And then screening and cleaning rejects, those are all considered stock prep or pulper area rejects. Then we have sludges, which are very different. They're much, much smaller particles, a lot of fillers and fines. We can get them from de-inking operations, or we can simply get them, if we're not doing de-inking, from clarifiers when we treat our water. And then also we can get biological sludges when we're using biological means to lower things like the COD, the chemical oxygen demand, or the BOD, the biological oxygen demand. Many of those sludges go and are burnt, incinerated, and the waste from the incineration, ash, cinders, flue ashes, and gypsum-type materials can be formed. And then we have other wastes that you might not think about that are probably smaller quantities and more irregular. Chemicals, used oils, cleaners, wires, felts, hazardous wastes. So we've got a broad spectrum of different types of waste, but this is a nice way to think about it and categorize it. Okay, the amount of rejects and sludges that are produced depend on the paper grade. This graph may be a little bit difficult to read, so I'm going to try and help you and go slow. Let's just see here. The graphic paper category right here, news, magazines, superior grades. The amount of total waste is about 10 to 25% for these materials. Why is that? Because we have to de-ink and we have to get rid of some of the other things like staples and materials, and so we've got a significant loss here in graphic papers. Then we can break it down into rejects and sludges. Heavyweight and coarse, we're getting about 1%, and then lightweight and fine from like fine screens or lightweight centrifugal cleaners, these kind of things. We're getting about 1% and about 3% from the cleaners and screens. And then the sludges, you can see for flotation de-inking, we're getting around 7 to 16% of our yield loss. And then whitewater clarification. So if we have a paper machine or we're just clarifying water maybe from the pulper system, we're getting about 1 to 5% loss. Now hygienic papers, they're actually, the hygienic papers are produced from office type papers typically in the recycling. Sometimes they're made brown tissue, like industrial tissue that's really not that nice, that we use actually in the university, and that's also used, so we can also use some boxes there. The amount of total waste, 28 to 40%. And the reason why that's so high is because the creping process in tissue making does not tolerate inorganic materials. Things like clay and calcium carbonate have to be essentially all removed if we're going to make tissue, because the creping process uses a creping blade. So typically what we have is we've got some kind of a blade like this, and we've got this, imagine this is a metal drum, dryer drum, and the paper comes down the dryer drum, and this metal blade scrapes that paper off, and the paper comes off and it crepes actually. And so this metal blade is always scraping this drum blade. Now if there's a lot of calcium carbonate and filler there, what will happen is that we'll start to damage the blade. It will wear out. And so we cannot tolerate any filler there. So going back to the table, we've got 28 to 40% total waste, and the major categories are going to be in flotation and in whitewater clarification. Okay, so basically flotation is giving us a category on the sludge produced from flotation de-inking, and whitewater clarification is giving us the category of where we're actually doing de-inking washing. Okay, so mainly that's involved with de-inking washing. Okay, then market de-inked pulp, we're going to use office paper. We're going to have yield losses of 32 to 40%, and we're trying to remove a lot of ink, and then the major losses are actually in flotation or water clarification from a washing system. Okay, so now we're going to some of the brown grades. If we go to liner or fluting, this material, it comes from sorted, mixed, recovered paper, supermarket waste. So, but basically it comes from old boxes. The amount of total waste now, 4 to 9%. So you can see for making recycling boxes, our yields are going to be much higher. That's good. And the reason why is because if you look over here, the sludges from de-inking, there aren't any because we don't de-ink brown boxes. So we get some heavyweight and coarse rejects, and we get some lightweight and fine rejects from cleaners and screens, plastics and things like that that come in. But you can see that our yields are going to be high, around 95%. Board, what we're talking about here is recycled board. That's multi-cylinder board, things to make shoe boxes, very stiff, thick materials. This kind of stuff is used to make children's puzzles. And the inserts in your 3-ring notebooks. We're going to use sorted mixed office waste, recovered papers, supermarket waste. Basically for this category of board, recycled paper board, we're going to use anything we can get. Okay, so it's the lowest level, it's the least expensive material, it's got the lowest quality. And because we don't have to de-ink and it's got very low quality demands, we're only going to reject about 4 to 9% of this material, and most of that will be in the rejects. Okay, so what you can see is that graphic papers, tissue, and market de-inked pulp all have a lot of de-inking going on, have to get a lot of contaminants out, and we have relatively lower yields. And then for the brown grades, for the liner board and the medium, the fluting, and for the multi-cylinder paper board, we're getting much higher yields, up to 95%. Okay, so now we can kind of talk about what is the source of waste and what is the composition. So in the pulper area, what we're going to get are larger objects such as plastic bags, metal wires, wood pieces, wet strength paper. Those are of course non-hazardous, and all these are actually characterized as non-hazardous. From high density cleaning, that's right after the pulper, and we're going to get glass, nails, paper clips, textiles, pins, staples. Then we've got our pre-screening. We're going to get things like plastics, polystyrene, stickies. These are very important. So for our screening, let's just call it screening rather than pre-screening. Well, it's called pre-screening because it's a coarser screening. We're going to get some big particles. Flotation de-inking, what we get rid of here is fillers, fibers, fines, printing inks, and stickies. Okay, now the fillers and the fibers, we don't intentionally try to take, and fines, we don't intentionally try to take those out, but they do come out unintentionally because we have to reject some foam, and some of this stuff gets caught up in the foam. Forward cleaning, we're going to remove high-density small contaminants such as sand, chives, hard particles, chips from UV colors and coatings, varnish. We're going to get rid of some fillers also too. Fine screening, we're going to get rid of little plastic fragments, lightweight contaminants, hot melts, stickies. Stickies are the important one. If we can get rid of the stickies with that fine screening, we're going to really protect our paper machine and the quality of our product. Okay, process water clarification, and this will typically come, a majority of it might come from washing de-inking processes. But if there's no washing de-inking, then we'll still have some water clarification. Anyway, in this, from the water clarification, we're going to get colloidal materials, fillers, fibers, fines, ink particles. And what you notice is that they're all non-hazardous, so we don't have too much of an issue in disposing them in landfill applications or composting. Okay, so if we look at some of the composition of reject samples, and recall rejects are the coarser, larger material that comes out near the pulper. What you'll see is we've got a lot of plastics, almost 50% plastics in our rejects. We've got some flakes and fibers of unpulped material, maybe wet strength. We've got wood, metal, and textiles. And that's for a newsprint de-inking plant. So this plant is probably bringing in newsprint and magazines. For a packaging paper like liner board, we're going to get a lot of plastic with the tapes and the foils that accompany the brown boxes. And again, we're going to get metal, unpulped material, flakes and fibers that can come from extremely high wet strength boxes or wax boxes, textiles, and plastics. Hard, so we're getting actually 74% plastics here, so quite a bit of plastics. It'd be very interesting to see if somebody could come up and say, okay, these are the plastics I'm getting. If I can grind them up and make something out of them, that would be interesting, or recycle them. But usually they're just disposed of in landfills. Okay, now let's kind of compare that with all those plastics and metals and wood in the rejects. Now let's look at the de-inking sludges. And what we'll see in the de-inking sludges is they're much smaller particles and more fines and fillers and clays and things like that. So if we look at this one right here, which was making a printing paper, and we're going to use a flotation process, what we're getting rid of is a lot of clay, a lot of fines and printing inks. Here's fibers at 7%, and here's calcium carbonate at 19%. So we're getting rid of a lot of the filler, and 8% is extractable compounds like pitch, stearic acid, flotation aids, things like that. Now, if we compare that with a tissue making process that's going to use washing, well, why is it going to use washing? Again, because we want to get rid of as much filler, inorganic material as possible, and washing will allow that filler to fall through the washing wire and come out, and that will protect our creping blade. If you look here, now we've got 26 and 20% of the inorganic filler, so we're getting large amounts of this inorganic material in our sludge. We're getting some fines and printing inks coming out from the washing, and we're getting some fibers, about 11%, and also some extractable compounds. Okay, now what I want to talk about is more or less focus on de-inking sludges. Okay, so these de-inking sludges can come from flotation or washing. We're going to do a little example where it shows it coming from washing, but similar thing for flotation. Treatment of wastewater. So where does our wastewater come from that we need to treat and reuse? Well, it comes from our clarifier. If we're doing a washing process, again, this is we saw this before, but we're pulping some recovered paper. It's going through a number 1 washer, number 2 washer, number 3 washer, and then finally the pulp, the cleaner de-inked pulp, is coming out here. And at the same time, what we're doing is we're taking our cleanest water here. It's going into number 3 washer. Then it's going to number 2, getting dirtier, and then the pulper in number 1 washer. So this right here, this stream right here, is our dirtiest wash water pulp, and that wash water, excuse me, and that's coming over here, and it's going into our clarifier. Our clarifier is actually generating the clean water that we can reuse, cleaner water, I should say, and it's also generating a sludge stream, probably at a pretty low concentration. Excuse me. So we've got our clarifier here, and it's generating a sludge at a low consistency. Now this is the sludge that I'm talking about that we'll focus on. All right. So we're going to have to, but before we talk about the sludge, let's talk about how it's formed. So really what we're going to talk about is our clarifier. And we're going to focus on a dissolved air clarifier that would be used in the mill to recirculate and clean water. So let's talk about water treatment. What we want to do is reuse a filtrate. Okay, so it's often going to be, that filtrate's going to be coming from a thickening or washing process, just like our diagram, and we need it to do it to conserve water. We just simply can't use fresh water all the time. So what's the objective of a clarifier? Well, it's to take that filtrate, make the sludge and a filtrate. All right, and that product filtrate's going to be cleaner. All right, now just in general terms, we talk about suspended solids, and that's what a clarifier does. A clarifier removes suspended solids. The filtrate to the clarifier, that dirty wash water in our example coming from the pulper, from the first de-inking washing step, 2,000 parts per million of suspended solids. So that's going to be the inks and the fillers and the clays and the fines and things. So we've got 2,000 parts per million of suspended solids coming into our clarifier, and our clarified water is only going to have 100 parts per million. So we've removed a considerable amount. That's going to be basically 99.5%. If my math is, no, we're going to remove 95%. let's see, 1 over 20, that's 95%. So we're going to remove 95% of the suspended solids. Okay? We're going to generate a sludge. It's going to usually be between 3 and 7% consistency, so we'll be able to pump that around. And here's something that you need to think about, because a lot of people get stuck thinking a clarifier is going to really clean all the material in the water, but it doesn't. The clarifier does not have the ability to change the concentration of colloidal or dissolved species. So what are colloidal or dissolved species? Things that are less than, much less than 1 micron. Colloidal species might be very, very, very fine agglomerates of stearic acid, for example. Let's think of something else. Well, that's probably the most common type of thing, some very small oil or liquid that's immiscible in the water. And then we've got dissolved species. What are dissolved species? Well, things like sodium chloride, salt. When we put sodium chloride crystals in the water, the sodium chloride dissolves. Okay? Now, if we ran that through a clarifier, the sodium chloride would not be removed. Sugar, when we put sugar in water, it's soluble, and we've got other materials in a clarifier that will also not be removed, like dissolved organic species or other types of salts. Okay, so we know now clarifiers are removing suspended solids, but they're not removing dissolved or very fine colloidal species. Okay, so here's a little flow diagram of how a DAF clarifier, this is called dissolved air flotation clarifier, how that's going to work. Here comes our raw water. So this is the water that we want to treat. And what we're going to do is we've got 2 arrows here, and both of these arrows are showing the addition of chemicals. So we're going to actually add 2 chemicals here. That would be considered a dual chemical system. So we're going to add chemicals, and those will mix in the pipe. And then actually this stream right here is clean water, but that clean water has in it mixed some air. Okay, so we've got the air mixed in with this clean water, and then so we're introducing air into this stream. So those 2 streams are going to mix, the raw water and the clean water with the air. And so we get very fine, fine, fine air bubbles. And those air bubbles are going to attach to the suspended solids. They're not going to attach to the dissolved material, and they're probably not going to attach to the colloidal material either. And so finally, this mixture with the chemicals, the raw water, and then the water with the air bubbles are going to come, the dissolved air, the very fine, fine air bubbles, come into what's called a DAF clarifier. And I'll show you a picture of this later. But really what we get are 3 products. The first one is some of the suspended solids, because of these chemicals, will flocculate and fall to the bottom. We'll have a scraper at the bottom, and that will be called our settled sludge. And then other suspended solids are going to float. They're going to float because of their density and because of the attached air bubbles. So those air bubbles will carry them to the top. We'll have some kind of scoop, and that will generate a floated sludge. So we've got our floated sludge and our settled sludge. Those are oftentimes combined as one sludge. And then the other thing that comes off the clarifier is our clean water. And I'm showing the clarified water actually coming from the bottom. It would be, it's probably not coming right off the bottom, but it could be actually that sludge, this settled sludge actually moves to the middle here, and this clarified water could come out from the outside, maybe from the outside of this tank or from maybe even the bottom. And so the clarified water is our product, and that's what we can use to go ahead and wash more pulp. Now, what happens with that clarified water is a fraction of it is going to go up here, and it's going to be reintroduced to air. And what we want to do is, why don't we just introduce that air to this dirty water over here directly? Well, it's because this air introducing process right here, if we had dirty water, the fouling of this equipment might be larger, and that would cause this equipment not to work well. So we tend to want to use cleaner water such that our air introduction system does not foul as much. So that's why we add air to this stream and then mix it. And so a small fraction comes here, is mixed with the air, comes into our, mixed with our raw water into the clarifier. So that's a DAF clarifier. This is what one looks like. This is a linerboard mill in North Carolina. And here's the clarifier. They can be either circular or rectangular, either one. So we've got a circular tub, basically. And this handrail kind of just shows you, that would be about 3 feet or so, 3 or 4 feet. And here's the floated sludge on the top, actually. And this thing right here is a scoop, and I'll show you another picture of that. So that's what a clarifier would look like. And here's the scoop and what the scoop is doing. This is the surface of the clarifier, and you can see, I told you it was a linerboard mill, and you see that the sludge looks a lot like the pulp fibers that are in linerboard. So mainly we're getting a lot of fines of linerboard. And here's that scoop. It kind of is a spiral thing, and it kind of scoops up the surface and then dumps it into a tray, and it's conveyed out. So there's your clarifier reject scoop. Okay. Now let's just kind of take a look at the chemistry in a very, very general way, but just kind of give you an idea of the chemistry of a DAF, dissolved air flotation cell. What we're going to do is we're going to add chemicals and the tiny air bubbles, okay? And what the chemicals are doing are, the chemicals are causing flocks to form. And the flocks forming help us in our flotation process. Basically, the larger the particle, the more air bubbles that are attached to it, the easier it is to float, and that's what we want. So what we're going to do is we're going to add chemicals to make many of these flocks rise to the surface. The same thing, we add the chemicals also, the flocks, some of the flocks are going to sink, and the flocks that have higher mass, that are bigger, are going to sink faster and more effectively. So our chemicals that we're using are helping us float some of the flocks, and they're helping us sink some of the other flocks. So we need to use those chemicals, and it makes a huge difference. We can go from a dissolved air flotation cell might only have a 50 or 60% efficiency without chemicals. When you add the chemicals, we go up to 95%, so it's a big deal. So let's just do a little cartoon simulation of what's going on here with the dual air flotation cell. So basically, if we play our little cartoon, the first thing that we find out is that here's a little particle that we want to get rid of in our wash water. And these particles, most particles in nature, carry a negative charge. Okay, so most particles carry a negative charge. All right, so we're going to have to get rid of these negatively charged particles, that is prominent in our system. So the first thing we're going to do is we're going to add a polymer. It's going to be a water-soluble polymer. That's that yellow thing that you see here, and there's a little red plus signs here to indicate that it's a positive polymer. So it's called a cationic polymer. And it's a highly charged cationic polymer, so it's got a very high positive charge. We know just from elementary days that positives and negatives attract, so opposites attract. So that highly charged cationic polymer is going to adsorb onto the surface of these negatively charged particles. Okay? So we formed a cationic patch, or a positive patch, on this anionic particle. You can see that there are other places on the particle that aren't covered, but we do have one little patch. This is the model that people usually think of. Now, to that, what we add is a second polymer, and that second polymer is shown right here. And that second polymer, this black line right here, has negative charges associated. So we're going to add not only the cationic polymer, but we're going to add a negative polymer. And that negative polymer is going to be a very high molecular weight polymer, so it's going to be very long, such that it can bridge two different particles. So it's going to be very long, so it can bridge those two particles. And that negative particle, negative polymer, is it going to be attracted to the negative part of that particle? No, it's only going to be attracted to that patch right there. So basically we're getting that negative polymer attached to that patch. And if there's another particle with, again, a positive patch on its surface, then we're going to have that negative particle attached to both of those positive patches. In other words, a strong flock is being formed. Now you might ask yourself, can we do this with could that cationic patch attach to another negative? Could we just use one cationic type polymer and attract these two together? Yeah, we can. It's actually found to be lower in efficiency. So we can use we can use this dual polymer system and it's much more efficient. Okay? So here we have our strong flock. We're just showing two particles together, but you can imagine that many particles can join this flock. And that would improve the flotation efficiency and the settling efficiency. So that's what's called a dual polymer system. Okay. So the other type of clarifier that we can look at are rectangular, and I've got some video here. This video was taken at a newsprint de-inking mill, and what we're seeing here is the surface of the dissolved air clarifier, and these bars that are going across are the rakes, and those rakes will scrape off the foam off the top. What we won't be able to see in this video is the clean water coming out, and we won't see the settled sludge at the bottom. So let's go ahead and activate this. So I'm going to go function F8. Okay, so here's our video, and then I'm going to run it. Okay, so what's happening here is these bars are above the surface, and they're coming over here to this. This side is the feed end, and that side is the rejects end. So the bars come over here, then they dip down in, and then you can see that this bar is basically submerged at the surface, and these bars are traveling in that direction, are going to carry the sludge at the surface to the rejects end. Oops, excuse me. I'm going to run it one more time, function F8. Okay, we'll just run it again. So you see these bars are above the surface, and then these bars right here, like this one right here, is right at the surface, and it's scraping that foam that's on the top. And it's not a heavy foam like flotation, it's a much lighter foam, or not foam at all, just sludge is going that way. Okay. So we've done that. So let's go function F8, function F8. Okay. Now we're going to look at here. This is the surface near the feed end, and this will kind of give you an idea of what the foam looks like and the sludge at the top looks like. So we will go function F8, and here's our video. Okay. And you can see there's air bubbles here. There seems to be a lot of flow here. And this right here is the beginning of that sludge that we're going to scrape off the surface. So this mark right here is probably where there's a lot of current because of the flow of the feed into that thing. And then this right here is that sludge that we're trying to get rid of, the suspended solids. Think about it. In that suspended solids, we've got our suspended solids, we've got our air bubbles, we've got our positive polymer, we've got our negative polymer. Okay, now let's look at the rejects end. So we'll go to a video clip with the rejects. This will show the sludge pretty reasonably. So here we have, there's just basically a dam or a weir here, and the sludge is going to be flowing over that dam into our rejects bin. So let's go ahead and run that. Okay, so there's that scraper bar. Okay, it pushes the material over the edge and then it returns. So here comes a second scraper bar, and there goes the sludge, and you can see it's being pushed over the side, about 3 to 5% consistency, and then that blade returns back towards the feed section, okay, and then a third blade, and this just happens continuously. And then, so there goes the sludge over the edge, okay? And it's doing a nice job there. I'm actually getting sprayed with a little bit of pulp every time that blade goes over, so a little messy. The other thing is, if you look back at that video, you notice what color this sludge is? This is a newsprint de-inking plant, and yeah, it looks like a very dark gray newsprint. So before, when I showed you that other picture of that clarifier, that was liner board, and you could see that there was a lot of brown fines and fiber in that liner board. So. Okay. All right, so that's the dissolved air flotation clarifier, and that's mainly the main method to recycle water in any type of de-inking process. So now let's just kind of look at, now we've got our sludge, and we want to just kind of say, okay, now that sludge at 3% consistency, we can't really do anything with it because we can't burn it, we can't landfill it, we can't put it in a river. We've got to dewater it, okay? And this table just is going to explain to us how different types of rejects and sludges are dewatered in a paper recycling mill. Now the first category, heavyweight and coarse rejects, okay? So what is this composition? Glass, nails, steel, wood pieces, wet strength paper. This stuff actually drains very easily. So really all we need to do is just use vibrating screens or just let it freely drain itself like the ragger. We don't even need to drain it that much, and it will drain to 80% solids. So because it's plastics or woods, it will drain pretty easily. And metals and sand, they don't hold on to the water. So they're basically almost a free draining material. So we only need the very basics, just some type of screen to hold the solids while the water flows off it. For lightweight and fine rejects, okay, let's think about what those are. Those are going to be sand, smaller pieces of textiles, fibers, coating colors, coating pieces, plastic fragments, hot melts, and stickies. The dewatering for those, we're going to just need, we're going to need some a little bit stronger. We're going to need screens, disc thickeners, dewatering drums, gravity tables, and screw presses. So actually, we're using the same kind of stuff that we're going to use for our sludges. We're not going to use all of these, but we'll probably use two of them. We'll probably use a disc thickener followed by a screw press, or a dewatering drum followed by a screw press. In fact, the screen, disc thickener, dewatering drum, and gravity tables will allow us to get up to maybe 20% consistency or so, maybe even less, and then the screw press will get us to the 50%. Then finally, the de-inking sludge, which is one of our main categories. And for de-inking process, remember, this is our largest area of yield loss. Okay, so we've got our fillers, our pigments, our fibers, fines, printing ink, and stickies. And again, what we're going to use are dewatering drums, gravity tables, belt filter presses, screw presses, chamber filter presses, centrifuges. So we're going to use we're actually going to use, usually in any operation, we'll use one stage or two stages. One stage, for instance, gravity tables or dewatering drums, will get us up to about 15% solids. And then if we follow that up by a belt filter or a screw press, we'll get up to 50 to, well, it's saying less than 65%, but 50 to 65% is a reasonable range. So the de-inking sludge is what we're going to focus on. Okay, so like we said, this comment here is that the ragger and rejects from the pulper area are not dewatered with special equipment. They are free draining. However, the sludges that we're going to look at, they use two-step processes in most cases. The first one is a gravity table or drum or disc thickener, like I mentioned before, and that's followed by a belt filter press or a screw press. So first let's look at a gravity table. Basically, we've got a little head box, and the head box actually just has that 3% slurry. We've got a wire here, a plastic wire. The sludge, the wet sludge, is put down onto the wire, And then we've got these little foils that come down, and what the foils do is they kind of they split up the sludge. They actually move it, kind of agitate it a little bit, and they split it here. You can kind of see where it's splitting down here, and that will increase the dewatering, because what will happen with the sludge is a lot of that, the water will leave the bottom, and then a filter mat of fines and fillers will form, and that will be, again, remember, two resistances to washing or dewatering. One is the wire, the second is the filter mat that we form with our fibers or fillers or fines. So these things are trying to break up that, that mat and just improve the washing efficiency. So you can see, and it comes down here, it starts off, it looks like oatmeal, and then at the end it kind of looks more like a drier kind of material. And actually I've got a video here that we can show this, so I'll just activate the video. Okay, so here's our feed end. So here's where we're feeding that sludge. You can kind of see it looks very wet. It's probably 3 to 5% consistency. And then if we run it, okay, here's our sludge coming in. Very wet. You can see the gloss on the top. These things are actually trying to break up that filter mat that's being formed. And then finally here you see these lines because that sludge is getting much thicker and more viscous. And now you see it doesn't look like liquid at all. It looks more like a wet sand or something. And then finally here's our solids at maybe 15–10%. So you can see that these this table is just draining that water out, and these foils here are just kind of agitating or separating and making new areas for the water to flow through and disrupting that filter pad. Okay, so basically what I just showed you was the gravity table. You can do this with a drum or disc thickener also, but I just had this example. This is this gravity table was again at that newsprint mill that I was talking. So it's a de-inking newsprint mill. You can see the concentrated material, those suspended solids, how black and dark they are. They don't look like newsprint at all. Well, they look like newsprint with a lot of ink in them, right? All right, so the second step, our gravity table gets us to about 10 or 15%, and then there's two major ways that we can do it. We can use a belt filter press or a screw press, and this just shows the belt filter press. Here what we can do is we've got two belts right here, one belt and then the second belt on the top, and then basically the sludge is added to this bottom belt. There's also some polymers. Some polymers are sometimes added to sludge as to help in the water removal. And then that we get some free draining of the liquid out of the sludge in the beginning. And then to remove more water, we've got to put it through these little presses. So we've got perforated rollers that increase the pressure between these two belts, and then the water kind of just squirts out. And then basically our drier and drier sludge comes out here, and finally at 6 we've got our dewatered sludge. Okay, so we'll take that out, and then this water right here, actually we're saying it's piped to a drain. So actually that is going to go to a sewer, and that sewer is going to run to a clarifier, and this kind of clarifier is not a dissolved air clarifier. But it's a water clarifier. It's a huge tank. It's going to handle all of the sewer lines from your recycle mill and all the sewer lines from your paper mill, pulp mill, any of the sewered water lines. So then that clarifier is usually outdoors. It's usually huge. It's usually, I don't know, maybe 40 yards wide, 40 meters wide in diameter, and that will be clarified. Okay, and the second way to increase the dewatering is using a screw press. In this case, that 15% material comes in here. That screw drives it up against this back pressure plate, and then the outlet of the higher consistency sludge comes out here. And we've talked about this as a thickening device, but here we're using it to thicken sludge. Here's a side view of a screw press. Basically, you've got, you can see some perforation here, but that's not the perforation that actually separates the sludge from the from going through the wire. Inside of this is another wire mesh that's finer mesh that actually does the separation of fiber and water. But basically, you can see that this sidewall is supported by these braces, so there's a lot of pressure in there. The water actually kind of flows out these holes here and falls down in the bottom, and the pulp is going from left to right towards the exit. This is a little video of the sludge press. This is at that same newsprint mill. I'll run the video, and it just kind of shows the water coming out the bottom. So here's the sludge press. The sludge is coming this way. The sludge is falling out the right side. And here we have that dirty water. And it really, if you can see it, it's really dirty. It's gray and dark. And that gray, dark water is going to go to the the sewer, and that's going to go to the clarifier. The clarifier is going to clarify it. And then actually that clarifier actually is going to either send it to a secondary treatment plant or directly dispose of it in a river or other receiving body. Okay, and then here's another video. This just shows what the sludge looks like, the product sludge looks like. Let me see if I can run this. Okay, so in this case, for this newsprint de-inking mill, they were going to take the sludge, and that sludge was going to was put in trucks, and then the trucks were going to transport it away. Okay, so let's just go back. See if I can do this. Okay, so here we have our video. I'm going to go function F8. Okay, and our video should be coming up.
No, one more time.
Okay, function.
Now you're on both screens, right?
Yes.
Okay, you've got to go one more time.
Thank you. Okay, so here it is, and then here's the video. And this is the sludge. You can see it looks very, very dry. 50%, it's very difficult to dewater to 50%. And even though it looks like that, it's got a lot of water in it. And we do not want to be transporting water around in trucks and spending gasoline to move the water around, and we don't want to be putting it in the landfills and taking up, you know, sometimes landfills charge by weight, but basically that we want to get it as water-free as possible. Now, if that material wanted to be, the other option is to combust it, to actually incinerate it. But that's what the sludge will look like. So we'll go function F8. Function F8.
Will combusting actually gain you any energy, or is it consume energy?
Yes, definitely.
So it's like black liquor.
Yes. So combustion is going to give us some energy, and we're going to talk about that. Thank you, though. That's great. That's just like having a nice, curious student to help you out. Appreciate that. So the other thing, typically you're going to either landfill or combust the sludge. Okay, and combustion's got a lot of advantages. First of all, when we do our combustion, we're going to reduce the amount, the volume of the material that actually will have to go to the landfill. So after we combust, we're going to get some ash, right? But those ash is going to be inert organic. That ash will have to be landfilled. But what the other things we're going to do is we're going to have some organics there. We're going to burn those. So we're going to make the organics in the final material inert, so it has no biological activity. We're going to also immobilize harmful material in the ashes and slags. That's a possibility. And then we're going to generate energy. So we're going to use, if we do this right, we're going to generate some good energy that we can use to help our mill. There's been a lot of increased interest in combustion lately because of increased cost of fuel and cost of purchase power. Landfill costs, if they rise, that's another incentive for more sludge combustion. Environmental regulations can impact how much interest we have in sludge combustion. And then finally, new combustion technologies with better flue gas cleaning. That's going to help us, at least with the environmental regulations, to kind of combust but be environmentally friendly. So in this process right here, I guess the words are going to be pretty small, but I'll walk you through it. We've got a sludge feed, and that sludge feed has already probably gone through a gravity table and through a screw press. And then that's going to be around 50% consistency. Then we're going to take that to a storage chamber, and we're going to meter that into a drum dryer. We're going to add some hot gases from natural gas and air, perhaps. And those hot gases are going to dry the sludge. The gases are going to come up here. We're going to use cyclones to try to remove any of the suspended solids in the air, and that dust will come down here. And then we're going to have a condenser that's going to add liquid and try to get some of the condensable organic material, perhaps, that has come off this dryer thing, because what we'll do is we'll heat up that sludge, and that will cause volatiles to come off, and we'll condense those in the liquid, and we'll then dispose of the air, or release the air after we've gotten those volatile organics out. Well, the solids from the drum dryer, they're going to go here, they're going to be mixed with the dust, and then they'll be stored, and then they can either be transported or actually sent to a combustion chamber. That combustion chamber we'll have some flue gas, we'll have some slag, some ash at the bottom, and then of course we're going to generate some energy that we can use, so that's a good thing. Okay, so these sludges, the final fates, final disposition, landfill and incineration, those are the two major ones that are occurring. Composting is another option. It's not as popular. It's much lower level, but you can do composting. Most of the sludges that we generate are not dangerous. There's not that much heavy metals in them. For details, you can look at some of the texts that will talk about the composition. In fact, I know of a tissue mill in southern North Carolina, and what they do is very interesting cycle. They recycle the mixed office waste into tissue, and the sludge that they get actually gets dried and applied to fields. And so it's used in an agricultural application. So actually, and that's a little different from composting, but it's used in an agricultural application. I think they grow corn or some other type of grain, and that corn is used to feed chickens, and those chickens are, of course, produced to feed humans. So basically, that kind of really lets you know how important paper recycling is to you, and how it can impact your life, because we're going from sludge to land to corn to chickens to you eating the chickens. So interesting application. There are other applications, cement, brick, concrete, other type of applications that are much lower in total use. And then you can come up with others. Some of the research that's going on is how to make valuable chemicals from sludge. How can we make ethanol? Can we ferment it and make ethanol? Can we make other chemicals from it? So there are other ones. But landfilling and incineration are the major players here. So let's just kind of summarize. Here's my summary slide. What have we learned about paper recycling and waste generated from it? Paper recycling generates significant amounts of waste, and we looked at it. Depends on the paper grades. When you do de-inking, you're going to get significant yield losses, somewhere around 2/3. When you do recycling of brown grades like liner board to make liner board or to make recycled paperboard, we're going to have yields up around 95%. That's real nice. There are many different types of waste that we generate, and we break them down into two major categories: rejects and sludge. The rejects include the plastics and the metals and all the very coarse materials that come from around the pulper from the beginning of the recycling process. And then the sludges usually come from water streams that we've treated, either from flotation or from washing, typically from washing. And that washing water is filtrated, is clarified, and that clarifier generates the sludge. And that sludge, we know, we need to dewater it. Usually it's a two-step process where we use a gravity table and followed by a screw press. Perhaps that gets us to about 50% consistency, and at that point we can transport it effectively and dispose of it, maybe in a landfill, or actually dry it and try and combust it. Several modes of disposal. We can do landfilling and incineration, and then there are others, but they're much more rare. Right now we're doing a lot of landfilling and some incineration, and as incineration technology improves, that's going to help the overall effectiveness of paper recycling and its effect on environment. And that will conclude my talk today on waste generated from paper recycling operations. Thank you.